modify the problem. Here we go. Notice for t equals 0, the switch is going to open. It's going to close here. So the source will be in the circuit. So we have to deal with that shortly and see how we're going to handle that. So I might be using this differential equation because you will have a source in the circuit for t greater than 0. You'll have an A. Again, as I said before, a lot of times instead of the switch there, we use u sub t, which is a unit step function, and u sub t will have a value of 0 for t less than 0 and a value of 1 for t less than greater than 0. So instead of using that, I can't really use it here because for t, again, because of that resistor being here, if I put 10 u sub t here, it will not work. Because 10 u sub t, that means this source is 0. I'm replacing this. I'm putting a wire when I use u sub t. I'll say it on the video one more time. Is it 1 micro or 1.5? What was it? 1 micro. Oh, I forgot to write, this is the 1.5 I sub 1. And I sub 1 was this current. This is I sub 1 again. 1.5 I sub 1. If I replace this with this one, they're not really the same. For t greater than 0, yes they are. The two circuits are not the same. Why? Because for t less than 0, this is what your circuit on the top is. Right? Because that's open. So that's gone. This is what you have, just this piece, 3 pieces or 4 pieces. But with this one, for t less than 0, this is a short circuit, you have the 6K, where in that one you didn't have the 6K. The good news is, if I don't have any sources in the circuit to power that circuit, what is the voltage across the capacitor as 0 minus? So if I'm looking for that, I can use that really here. It's the same thing in terms of VC 0 minus. But circuit-wise, they're not the same. That's still a 0.
What about the dependent source?
Well, nothing's going to happen if I don't have a source to power it. So for t less than 0, my voltage across the capacitor, because there is no source here, my source is dead. This was open. Nothing going to it. You're looking at this. This by itself is not going to do anything unless there's another source to power it. So now the voltage across the capacitor is going to be 0. There's no current going anywhere in any of these. Now let's look at it for t greater than 0. And what you're going to have is this circuit actually right there. Because for less than 0, this was a 0. For greater than 0, I can combine these two into one resistor of what? 8K. That current is the same current going through them. 1.5 times I sub 1. This is I sub 1. Capacitor, 1 microfarad. This is 6K, and this is 10 volts. I'm looking for the voltage across the capacitor. What is the voltage across the capacitor here as a function of time? Notice I can use source transformation right here, because I'm trying to shrink that circuit a little bit there. If I do source transformation, I will have what? 8K. (1.5) I sub 1, and I sub 1 is right there. This is 1 microfarad plus minus VC. This will be a 6K down here. This will be a current source pointing upward, and what's the value of that current source?
10/6.
10/6. Notice this is not a source-free circuit. All the examples we did last time, we did not have a source for t greater than 0.
It's 10/6K.
10/6K, yeah, would be milliampere. Thank you. 1/k is a milli. So now let's look at that. I can do KCL, assign current leaving, coming in the direction you want to. Current coming down, I sub C. We'll call this what? I sub 2. All the currents entering that node, the top node, should equal all the current leaving that node. What's the current entering the top node? 10/6K. What's leaving that node? I sub 1 plus 1.5 I sub 1 plus I sub C plus I sub 2. Clean the math. 5 over, well, I can leave it 10/6K because, let's see, well, it doesn't matter. 5/3K equals 2.5 I sub 1 plus I sub C plus I sub 2. And maybe I can write I sub 1, I sub C, and I sub 2 in terms of the voltage. Well, they're all in parallel. They have the same voltage across them, which is what? VC. So I sub 1 is VC divided by what? 8K. I sub 2, it's VC over what? 6K. And I sub C, I equals C dVC dt. So if I replace them all with their equivalent value, I'll have one equation by one unknown. That's 5/2, right? Times I sub 1. What's I sub 1? VC over 8K plus I sub C, which is C, 1 micro, times dVC dt, plus I sub 2, which is what? VC over 6K. LCD, I think 24, is it? 24K? Maybe not, because that's 2 times 18. 48 maybe.
No, you're right with 20.
Because that'd be 16. That wouldn't do it.
Oh, yeah.
That's 16. Because if you look at this, that's 5/3K equals 5 VC over what? 16K plus 1 micros, that's what? 1 over a million, right? dVC dt plus VC over 6K. So I think the LCD for these numbers, I can leave the 1 micro here, it's not a big deal. I'm not worried about that number. Let me multiply it by 48K. What's 48 divided by 3? 48 divided by 3 is 16. 16 times 5, this will be an 80. 48 divided by 16, 3, is it? 3 times 5 is 15 VC. 48,000 K times 1 micro. I got 0.048, right? dVC dt plus 48 divided by 6, which is what? 8 VC. And if we collect like terms and clean it one more time, I will have what? 0.048 dVc dt plus 23 Vc equals 80. I want to make that number 1. Why? Because the solution I gave you, what's the coefficient here? 1 for both of them, right? So I need to make that number a 1. If you can see it here. That number was always a 1, this always a 1. So to make it a 1, I'm going to divide both sides by 0.48. .048. So dVc dt plus 23 divided by 0.048, roughly 479 is 0.16. I'll go 479, that's fine. What's 80 divided by 0.048? And I got 1667. Now that matches this differential equation. The differential equation says if you have an equation that looks like this, if you have that, then your solution to that will be A over alpha plus some constant which we'll have to find, e to the negative alpha t. That's what that little sheet I wrote there. That's what you have. So in this case, my solution to this problem is going to be what? Vc as a function of time. I don't know why I wrote slash line. There's no line here.
Is that cheat sheet on Blackboard?
I didn't put it yet. No, it will be. Vc equals what?
1667 over 4.
Yep, 1667 over 479 plus some constant e to the minus 479t. 1667 divided by 479, 3.48 plus some constant e to the negative 479t. This is for t greater than 0. Well, how would I solve for k? So right now, I need to solve for k. How would you solve for that? I need to know something else. We have something else. We looked at the circuit for t less than 0. What was the voltage? 0. Well, we know with capacitors that the voltage of 0 minus is the same as the voltage of 0 plus. So the voltage of 0 plus then for the capacitor has to be 0. It has to be. So come back to this equation now. Plug it in. Let t be 0. So 0 equals 3.48 plus k e to the negative 479 times 0. Isn't that a 0? And e to the 0 is what? 1. So what's k equal to? Negative 3.48. So what is now the voltage across the capacitor for any time for t greater than 0? Is going to be 3.48 minus 3.48 e to the power of negative 479t. And that is my solution. Notice this is not a source-free circuit. This circuit has a source in it for t greater than 0, and that's where that piece came in. All the ones we did last class, we did not have a source for t greater than 0, so you did not have that piece. So a little bit different there. Trying to find something that looks like scary a little bit there. Picture. What time is it? Yeah, we got time for it. The only thing I don't like about that problem is a capacitor, so I'm looking, maybe I can find an inductor there, so we're not always doing capacitors. I found one. I was about to do this problem. I got excited when I saw this problem. But again, it's capacitor. And again, some of these resistors will combine together, so let me do an inductor. So I looked, and that's not a bad one. So let's go to that one. It's not as big as the other one, but at least has an inductor. Remember, when you have a capacitor, you always want to find the voltage across the capacitor for 0 minus. Why? Because that's the same as the voltage across the capacitor is 0 plus. When you have an inductor, what do you want to do? You don't want to find the voltage across the inductor. You want to find what? The current through the inductor. Because the two things are always consistent. With an inductor, I sub L as 0 minus equals I sub L as 0 plus, in case you forgot. With the capacitor, VC as 0 minus equals VC is 0 plus. So when you have a circuit that has a capacitor in it, you want to find the voltage across the capacitor is 0 minus. When you have an inductor, you want to find the current through the inductor is 0 minus. We also know quickly V for an inductor equals L di dt. And for a capacitor, I equals what? C dVc dt. So when you have a capacitor, you're really looking for KCL, nodal equations. You'll see me, I use nodal equations for them because I'm looking for the current. When I have an inductor, I'm looking for the voltage. So what am I going to use? It's not going to be nodal analysis. What's going to be? Mesh. That's how I try to tackle the problem. Because of these things. So let's take the next problem and see what will happen. I'll put an inductor here. So we did capacitor. Let's bring an inductor here. Leave a space on the left a little bit there. At t equals to 0, that switch will swing. I have 100 milliamps, so that's 0.1 amp. I'm not going to put 100 milli. Make it 0.1 is easier. I have 30 ohms here. I have another current source of 0.2 amps pushing up here. I have a resistor of 40 ohms. And I have an inductor here of 30 millihenry. The question, what's this current? What's the equation for this? I. They want to find the equation for that. Well, notice these guys are connected how? In parallel. So if I know the voltage, I can find the current. So I'll see what I need to do with that problem. First, I have to look at the circuit for t less than 0. So that's my first step. Look at the circuit for t less than 0. And if you have an inductor in the circuit, what do you want to find? I sub L as 0 minus. These are the steps. If you have a capacitor, what do you want to find? V sub C is 0 minus. That's the first step always. So what do we have here? Capacitor or inductor? Inductor. So I need to find I sub L is 0 minus. Notice this is open, so this piece is really not a factor. It's not anywhere in the picture. Because that's open. Nothing goes up there. They just circle like this the whole time. It's not going to affect that side of the problem. So if I look at my circuit that way, this was going to look like 0.2 amps, $40. And what's going to happen here to that inductor? To a DC, the inductor is going to react as what? Short circuit. What is the current through the inductor in this direction? This is I sub L as 0 minus, which is what?
0.2.
Yep, 0.2 amps. All that current is going to go that way. Why should it go through this one? Least resistive path. What's this current here then? Nothing going through that. So for t less than 0, assuming this sat for a few seconds, you built it, you went to get a cup of coffee, you came back, you start measuring current. There would be nothing going through that, all the current going through that one. And it's sat there the whole night, left it running, you forgot about it. Now it's the morning, you come in and say, oh shoot, I forgot to close that switch. So now let's walk in, close that switch. Let's look at the circuit for t greater than 0.
How come 40 is not part of the circuit?
Because that's open here. There's nothing going that way. That current's just going to loop right there. It's not going to affect the inductor or any of these. So step number 2, let's look at circuit for t greater than 0. Now that switch closes. So that will affect the circuit. So now my circuit will look like this. 0.1. I can put the 30 here. It doesn't really matter if I put it on the side or the top or the side. That's 0.2 amp. That's 40. And that's 30 millihenry.
So because we're adding a new source, that's why the inductor is actually what matters in this one?
No, the inductor didn't. Well, I'm just looking at it for t greater than 0. Now, for a few seconds, yeah, because you have this as for a few seconds going to charge. Then after that, that goes back to short circuit again. But for a few milliseconds, we'll calculate that. Your 5 tau. Remember the 5 tau?
Yeah.
So during that 5 tau, that inductor is no longer just a short circuit. But after the 5 tau, it goes back way to a short circuit. And again, the question, what's I? Well, if I know what the voltage here If I know what the voltage across the inductor, can I find what I is on the in parallel? So that current is going to be 40 divided by, V divided by 40. So if I know my voltage, I'm done. I equals the voltage across the inductor divided by 40. So I shift my focus now, not on finding what this current is, find what the voltage across the inductor. Now I can make a few simplification to that problem, and one of them is what? I can combine these two sources together, that will make it what? 0.3 amps. I got these two resistors, how are they connected? In parallel. Since I don't care about the current there, I'm interested in the voltage. Product over the sum. What's 40 times 30 divided by 70?
17.14.
17.14, we'll go 17 is good, to make the math easy. Now remember what I said early, when you have an inductor, you want to do what? Mesh analysis. This is not going to be a good mesh analysis there. You know, I could do it here, but I can do a source transformation quickly. If I do a source transformation, you'll have one loop there, and you're done. So let's do a source transformation here. 0.3 divided by 17, which is what? Nope, that should be a voltage source now.
We'll multiply
0.3, yeah, 0.3 times 17, thank you.
5.1.
What is it?
5.1.
5.1 V equals I times R, Ohm's law. And now I can do a mesh equation here. And this is my voltage. The current going through that is the same current going through the inductor. So sum of the voltages in a closed loop is 0. What do we have? Negative 5.1 plus 17 times I sub L plus the voltage across the inductor. What did I say the voltage across the inductor? L di dt. Equals to 0. Clean it. 30 millihenry. What's that? 0.03? I think 0.03. DIL dt plus 17 I sub L equals 5.1. DIL dt plus I keep forgetting which side is up, which side is down, because I scanned them. 17 divided by 0.03 is what, 567 roughly? And 5.1 divided by 0.03, 170. Again, the reason we got that is no longer a 0. Why? This is not a source-free circuit for t greater than 0. We have a source in it. That's the reason for that number. If I didn't have that, that would be a 0. So the solution now, I sub L as a function of time, is going to be 170 over the 567. It's always this one divided by that, plus some constant, which we'll find it in a minute, e to the power of negative 567t. 567. 0.2998, how about 0.3? I'm not done with it, but let me go back and recap. What was my first thing? I looked at the circuit for t less than 0, and I got the current as 0 minus. I looked at the circuit for t greater than 0. What I should have said here, write a first order differential equation. Write a first order differential equation. So if it doesn't matter if you have capacitor or inductor. If you have an inductor, your differential equation will be in terms of the current. If you have a capacitor, it will be in terms of the voltage. So now you get your solution. Step number 3 is what? Find K. Solve for K. Well, how do you solve for K? Again, you're going to look either use I sub L as 0 minus or VC as 0 minus. It depends what kind of a circuit you have there. In this case, we have what? We have I sub L as 0 minus, which happens to be what? 0.2? If you look at the circuit for t less than 0, is that a 0.2? So I sub L as 0 minus equals I sub L as 0 plus, which is 0.2. Now I should be able to solve for K. 0.2 equals 0.3 plus K e to the power of negative 567 times 0. Point 2 equals 0.3 plus K e to the 0. What's K? K is negative 0.1. So now my current, or my current through the inductor equals what? 0.3 minus 0.1 e to the negative 567t for t greater than 0. Big deal. That wasn't the question. The question was to find the current through the resistor, that resistor, not that one. I said, well, you know, if you know the voltage, you can find the current, right? Well, can I find the voltage across the inductor? Let's see if you remember. V equals what? L di dt, right? Take the derivative of the current through it, you get your voltage. So that's the last step there. The last step is now solve for whatever they're looking for. Step 4, what we found here is the current through the inductor, but that's not what they're looking for. Solve for, what should we say? Whatever they're asking for. What the problem asks for. So solve for what the problem asks for. What did the problem ask for is the current through that. I said, well, here I stated, I maybe not, if I know what the voltage across the inductor, I can find that current. It's VL over 40. So let me find what the voltage across the inductor. V, or VL, equals what? L di dt. And what was L here? 30 millihenry, 0.03. And let's take our calculus skill. What's the derivative of this? 0. Minus times a minus, that would be a plus. 56.7, right? E to the power of what? Negative 567t. You agree with that? This times that, e to the negative. So now 0.03 times that number, (1.7) e to the negative 567t. That's the voltage across the inductor at any given time. And once I have that, divided by 40. So the current through that 40 ohm resistor, is it 40 ohm or 400? 40 ohm is going to be VL as a function of time divided by 40. So it's 1.7 e to the negative 567t divided by 40. If you look at our book, they don't do them this way. They make you memorize all this stuff. I like to derive everything. I don't want to memorize, oh, if this is this, do that, beside the equation. I like to see them step by step, what's happening there. So that's 42.5 e to the negative 567t in milliamp for t greater than 0. And we know for t less than 0, what was it for t less than 0 for that problem?
How do you know it was milli?
That number is 0.0425. We did that part when we looked at the circuit for t less than 0. So if I'm watching the current actually through that resistor, I sub 40 ohm, for t less than 0 was like this. Then, for t is greater than 0, 0 or larger, I went to 42.5, that's the 42.5 milliamp here. And it went like this. So it jumped up there, and it came down. The question early, are we looking at this because we have another source here? Is that why we're looking at it? I remember that question because we treat that inductor as a short circuit. They go, okay, once you flip that switch, how come we're now looking at this as a short circuit? I said, it will be a short circuit if you let it sit for a few seconds. But I'm looking at it before it settles down, right there. Well, how long is it going to take it to settle down? This is 5 tau before it goes to 0, before it becomes a short circuit. It takes 5 tau. What's tau? Is 1 over that number. That's going to be 5 times 1 over 567, which is 5 over 567 seconds. What's that number? We're talking about 0.0099 milliseconds. That's it. After the 9 millisecond, that becomes a short circuit. So that's the only part I'm actually looking at between the 0 and the 9 millisecond. What's going to happen to that current through that? After that, the inductor becomes a short circuit. And if the inductor is a short circuit, let's look at that circuit again. If the inductor is a short circuit, guess what? How much current is going to go through these? Nothing. Because they're all going to go through that short circuit. Why would any of these currents will go through this or that if that's a short circuit? So after 9 milliseconds, this is a short circuit. No current going through this, no current going through that. The voltage is 0. So that's how we handle a circuit that's not a source-free circuit. All the problems we did last class and today, all of them were either RL or RC. We did not touch RLC. You're in for it next class. And it will take us probably the entire class to do one problem or close to that. Plan on 6 to 7 pages of problem. RLC circuits. You know, so they're a lengthy process.
Even if it's like a pretty simple,
Yep, you'll see. You'll see how long it's going to take.